Good morning. Good morning, everyone. So now we finally get busy with something practical. Um, we have refreshed quantum mechanics. We looked a week ago on identical particles and understood that the wave functions are rather complex. One has to symmetrize and anti-symmetrize those. So we'd better get to something which does not involve these complex functions. So today we will learn a method with which we can actually proceed with advanced quantum mechanics without much of complexities. Right? This method is generally called second quantization. It involves creation and annihilation operators. So most of the time I will talk about this creation and annihilation operators in different facets. I will tell you how to navigate in Fock space with the help of these operators, how to reveal its structure. Another facet of creation and annihilation operators are field operators. We will learn what is this. And we will make the Hamiltonian in terms of creation and annihilation operators. Otherwise, they're useless, right? Hamiltonian three particles, and we will talk about interaction. We will reveal something about Heisenberg equations. And that will be done an example of Fermion, of bosons first. Then, at some point, I switch to Fermions. Most of the outlining will be the same, with few exceptions, important exceptions. So we will talk about differences and similarities. And in the end of the lecture, if I come to the end, because actually I have almost infinite number of slides, but those are simple and can be taught quickly. In the end of the lecture, I will present a table where all things we have to know about second quantization are collected. Fine. As usual, please put the questions to the chat. I really like it because it's one of your feedbacks I can get from you. And let's go. So creation and annihilation operators. Let us see where we are first. First of all, we define a basis in the space of a single particle state. I will label this state by some index K. An example of such index is a numeration of plane waves with a wave vector K, but it doesn't have to be wave vector. It's just some index which labels a set of single particle states. Right? And now I recall Fock space. Now I recall Fock space, and what we want to know about Fock space, want to recall that it the basis of this state is made of so-called number states. So it is a wave function which is labeled by a long row of occupation numbers. So for all levels which are there in the system, we define occupation number. And this long row of integer numbers will give one of the basis states of the Fock space. One can say it's a bit complex, but if you recall how we derive Fock space, how many states we have actually got rid of, it's just a blessing. We have only states which we really need, nothing more. Good. This basis is orthogonal, which means that, yeah, if these sets are different, the corresponding wave functions are orthogonal. Fine, that's where we are. Now let us define an operator. Let's see. No. Something strange. Okay. Let us define an operator. I will talk about annihilation operator. What does it do to the wave functions in this space? If there is a particle, at least one particle, at the level k, it takes it away, right? Formally, you jump from one basis vector to another basis vector because you change the set of integer numbers which characterizes the basis vector. So this is logical. What is less logical at the moment, that simultaneously wave function is multiplied with this factor. I always find it strange when I was a student. But let us accept it. Let us accept it for the moment. And then we will figure out that eventually it's very useful, ugly square root. Good. That is annihilation operator. Let us now formally define emission conjugation of this operator. So we have operator A, we have operator A dagger. If we conjugate, let's see what we do. It's written here. We do complex conjugation and permutation of the indices. So what was initial state becomes final state. This is why the conjugation operator adds a particle to a given state. It adds a particle to a given state, and by conjugation, yeah, there is a similar square root appearing in the front of the expression. Okay. So here particle is extracted, here particle is added. Okay, look here. Good. So for each level, for each basis element of the single particle state, we define an individual operator of creation or annihilation at this particular level. Okay, I've forgotten to say that this is creation operator, but yeah, I guess it's clear from the definition. By Degger, okay, it's kind of, yeah, there is a story about this. Let me tell this. But yes, it's Degger. It's Degger. And when I was a student, I always mix them up. I didn't remember which operator is annihilation and which is creation. All right, so one has to memorize it somehow. All right, the idea of memorization depends whether you're kind of appreciate your Christian roots or not. All right. One of the points of the confusion that if you're kind of it's not about your belief, it's about your roots. Usually, cross is used in Christian cultures as a sign of death, right? So people sometimes tend to believe that this brings particles to the end. However, it's not so, and one can justify it, kind of memorize it by two ways. If you kind of don't care about your Christianity, then it's plus. So this operator adds a particle, creation operator. Well, if you're kind of deeper about Christianity, then you should understand that cross symbolizing death is eventually also a symbol of a new life, symbol of recreation. So this is why it is a creation operator. Let us see a question from Sarah. How can you logically see that this is what the conjugated operator will do? Because, as I said, by conjugation, I flip the states. So if operator A works on the state and transfers it to the state with n plus particle, conjugated operator takes the state with n plus particle and removes one particle. Yeah, this is it. Okay, good. So we define the separators. And let's do some simple algebra with this because, yeah, the only way to understand what is this, how useful this is to do something. Let's do something. Let me look at the products of conjugated operator and of creation annihilation operator. Let's compute what is, for instance, Dega A. Okay, how do we do this? Well, we just plainly apply the separators. So I apply annihilation first. I got a square root and one particle less. And right, I apply this. Since I have deleted one particle, I have to multiply it with square root of n once again. So what I get is nk. So precisely the number of particles at this particular level, at this particular in this particular basis state. Right. So the operator is diagonal in the basis which we have chosen, in the basis of number states in Fox spice. Right, and its matrix elements are conveniently occupation numbers of this particular level. right? So if I want to compute occupation numbers on some system, we could just concentrate on this quantities. All right, so it's separator of the number of particles at particular level. If we sum up over all levels, naturally enough, we got the total number of the particles. Fine. So at least there is some use of it. Let us do something else. Let us change the order of the separators. It is important that creation and annihilation operators do not commute. Again, one can just plainly compute this. So we again acting it in this order. We have n plus 1 at this particular level. Please pay attention to the fact that it works only on particular level. It doesn't do anything with all other levels. Okay, and right then it comes twice since we have increased the number of particles. So in total we have n plus 1. Right. What does it mean? It means that the difference between these separators, between these two products, or let me put it differently, commutator of these two operators is 1. Great. It's a simple commutation rule we have established. That we will apply 1,000 times during this course. Let us go further. Commutation rules. Let me formulate it in a wider context. Let me compute commutators, not only of operators at the same level, but at all other levels. And luckily enough, all these operators do commute at different levels. That's how I write it. That's a Kronecker delta function. So it's zero. It is 0 if k is not k prime. The same one can see this concrete calculation that also two annihilation, two creation operators do commute. Fine. The point is, one could use these commutation rules as the basis of the theory. If you kind of wanted to make a little bit more elegant theory, we could postulate commutation rules and go on. We can show that operators which obey these commutation rules kind of create particles and elect particles. But I find it rather than physical, so I prefer to introduce these operators first in explicit way. Fine. So we got to commutation rules. Let us see more questions. Let me talk about the structure of the Fock space we are in. Let me understand the following. Let me understand that one can go from one basis vector to another basis vector with the help of the separators, just applying the separators. Yeah. So let us start with a particular state we have found the important vacuum state. Right. State with no particles. Eventually depends, because really soon we will define vacuum as a state of this big number of particles. We need a little bit more formal definition of the vacuum. And here it is. We will also use it kind of as a operational definition of the vacuum. It's also rather physical. One cannot annihilate anything in a vacuum. There's nothing to annihilate. So for all operators, if it works in vacuum, the result is undefined. Usually, if you take an operator and work in a wave function, you expect something, right? You expect a vector, which can be normalized, which can be wave function itself. So the only way to say this operation does not make sense, this operation doesn't work, is to say that the result of this action is zero. That's something which is not wave function because you cannot normalize it. So this is the definition of vacuum. If you try to annihilate anything, it's just no wave function. It does not work. Fine. We can create. We can create, and we can apply this operator subsequently in all levels, and in each level we apply it nk times, creating all particles we need. Luckily enough, these operators do commute. These operators do commute, so it doesn't really make a difference in which order we create these particles. Yeah. Okay, so then there will be also a factor, normalization factor, right? It is made of all these ugly square roots, which we put into the definition of operator. So one has to divide it. That is something which we have seen. It's actually a degeneracy factor. How many different states you can have before symmetrization or anti-symmetrization. Before symmetrization, we are talking about bosons. All right. So any state can be constructed with the help of these creation operators. Let us see how to draw this. It's good to restrict yourself only by two levels. And in this case, you can draw all basic states in a two-dimensional plane. That's what I did. Right, so this state with no particles, one particle at the level 2, and so on. You understand this? Good. So what are creation operators? In this case, creation operators just moves in this lattice either up or to the right. Two creation operators for two levels. So, for instance, you can create a particle in first level, then created to the second. In the second, as I mentioned, you could do it in other way around, in different sequence. It doesn't matter. You will open to commutation of these operators. You will come to the same state. Fine. So there's a structure which is somehow in between a tree of a grade. With a tree would never come to the same node. With a grade you can come many times. That's how it works. How to represent it for actual situation when we have infinite number of levels. Let's see. I think I have question. Applying the creation operator to a vacuum can give you occupation of any level based on the power which you use. Yeah, this is logical. So let's work on level 3. We apply a 3 dagger once, we got 1 particle. We apply it twice, we got 2 particles, 3 particles, and so on. That's how many times we apply the same creation operator. Right, and this in this picture, it means that we just go to the left or to the right. So they combined in powers. Good. So I actually put the answer how to present it for infinite number of states. Several years ago, students had a reasonable notion of web design. I don't know about now. So can anybody guess how to implement Forkspace with a website? Infinite Forkspace.
I guess it kind of allows you to click through all the different parts of the website. So you can go from one level to another level to another level and then go back.
Then you would have to have an infinite website, which is not very practical. Routing problem. In this case, you would have to have an infinite number of websites to route. The answer is PHP. Dynamical creation of web pages. You don't have to have infinite number of pages in order to show to the user an arbitrary page. Someone would make, for instance, a web page of vacuum state, put some links like increasing this level, creating an operator in the level, creation operator in level 1, creation operator in level 2, and the possibility to choose any level. Okay, you click this link, you go to a new web page. There you have also a number of links which would allow you to create particles. And also for the state, you're allowed to annihilate the particles. So it's a dynamically generated web content which you can use in order to illustrate in many details the actual structure of Forkspace. Did you get it? Shall I explain once again? Many websites still work on this principle. They dynamically generate what you want. Fine. Let us move forward. Let me turn to a more flexible and sometimes more useful representation on these operators. Okay, what we did, we defined these operators, annihilation operators, in a certain basis. The basis of some eigenstates in single particle basis. We could have some Hamiltonian in single particle basis and define the levels. But as we discussed, quantum mechanics is a very democratic science. And one has a freedom of choice of pictures, freedom of choice of the basis as well. Kind of all bases, which we can imagine, are equal with respect to quantum mechanics. So we want to understand how these operators would look in another basis. That is again to do. Let us try a particular useful representation. Let us try coordinate representation. Let us first recall how wave functions are transformed upon the change of representation. Yeah. So if wave function in the representation of the levels, it's just a set of numbers ck corresponding to each level. To get it in our representation, well, what shall I do? I shall take basis vectors, which are in our representation. For each level, I have wave function, and it is summed up with C's, with amplitudes. So it will use wave functions of the basis states. All right. So the operator in other basis, in particular representation, coordinate representation, is similar. In fact, instead of components of wave functions, we use these operators. And we come to coordinate representation of creation and corresponding annihilation of annihilation corresponding creation operators. Let us see the questions. Same question as Sebas. That's interesting. What was, oh, what did you write in blue next to N? I guess it was several slides ago. Let me go down. Here. Do you mean here? Sebas. Of course it's gone, but I still remember what I wrote. So this illustration, obviously, for two-dimensional space, when we have only two levels. What I wanted to understand, what happens if I make a larger dimension, if I also add n3 and 4 and so forth. if I include more levels and actually infinitely many levels. That's what I wrote here. Good. Let me come back to field operators. Field operators. Sir, it's an operator in coordinate representation. To get it from operators in the level representation, one needs to utilize wave functions of these levels in coordinate representation. So that's how we make what I will call field operator. So this is an operator which annihilates particle not in a level, but rather in a point, in a particular point of coordinate space. Correspondingly, psi dagger creates a particle at this point. So everything is logical. Just to note, it's just a particular example of our representation. It's a convenient, we will use it, but we could think of any other representation, for instance, momentum representation, representation in the basis of the states of harmonic oscillator. Tell me that. Fine. Field operators. How good we are doing on time. Oh, that's not bad. Let me derive commutation rules for these field operators. Since they're made from creation annihilation operators set, and one knows commutation rules for those, one can kind of compute them directly. Let me just give you a result, because it's also logical. So these operators commute in different parts of the space, but they have commutator which is delta function. So it blows up if these two coordinates are the same, right? That corresponds to the picture of levels. They commute at different levels. They would give you one at the same level. Fine, and two field annihilation operators, two field creation operators, they commute. Good. But this we can make another operator which we'll use. It's a density operator. This is similar to occupation number of the level, but now we look at occupation not in the system of levels. We look at the occupation in particular point of the space. So we get density operator. Fine. And let me go on. Perhaps I can have time to explain non-interactive Hamiltonian as well. Look, it would be just toy, these operators, if you could not do anything useful. Anything which is useful should be related to the Hamiltonian, because the Hamiltonian is the operator which governs quantum dynamics of the system. It defines all states and properties of quantum system. So we want to have the Hamiltonian in terms of creation and annihilation operators. That appears to be possible, and this is big advance. If it were not possible, it would not make sense to talk about creation annihilation operators. Okay, how we can get it? Hamiltonian is a kind of representation of an energy. Yeah? And energy in terms of occupation numbers, as we talked about this, It's just the sum of individual particle energies. So for each level k, we take as many particles as is there and multiply it with the corresponding energy of this level. Fine. Now let us kind of quantize this. Let us replace these numbers with operators. Okay, so energy becomes Hamiltonian. And occupation number as an operator, luckily enough, I can express with the help of creation relation operators. Here they are. Here they are. So we have the Hamiltonian in this form. Looks a bit strange, was it's a sequence of annihilation creation, but this is to represent occupation numbers. So another exercise, again, it's an operator in terms of the level creation relation operators. You could think of a coordinate representation. So let us express this in terms of the field operators. Yeah, I screwed up a bit. That has to be conjugation sign. Fine. Good. So basically, one can do it by direct algebra. One can express field operators in terms of A and actually revert this relation using the completeness of the basis of the wave functions. So after reversion, we see that creation annihilation operator, it's yeah, again linear combination of those, and it's expressed in terms of basis vectors. Good. Now we take this, we put it here, and that's what we have. As you see, these wave functions has been evaporated from this expression. Why? Because I now write down explicit Hamiltonian in coordinate representation. So instead of E K, which works a particular level, I write the whole Hamiltonian. Good. So the form seems logical. So we recognize kinetic energy and potential energy. So I can think of separate operators of kinetic and potential energy. It is quadratic in terms of creation operating and annihilation operators. So we find it here and here. What can be confusing is an integration over all points. But that's also logical because these particles can appear in any point, disappear in any point. So that's one has to take all points into account in this Hamiltonian. Right. This is for momentum. The same form holds eventually for any other one particle operator. For instance, if one thinks of operator of momentum for all particles, how one can make it summation over dr operator psi of R, and now we have operator of momentum in coordinate representation. So that would be, I need to shift something. R D R. Now I have to put H bar somewhere. I put it here. And all this, don't forget, there's no numbers, they're operators. Good. So this is operator of the total momentum. As you see, it is totally in line with operator with a Hamiltonian. Right. I guess there is a need for a break. So let's have 9-minute break till let's see. Yeah, 9:14. 9 minutes break. I guess I stop the video. And for this, I have to stop share. Let us start again. Oh, I have to share more screen. So what we did, we get Hamiltonian of the particles without interaction. We did it in representation of the levels, and we did it in coordinate representation. In both times, separators are quadratic in creation and relation operators. Let me add important part. Let me add interaction, and also, okay, let's do it with our hands. How does it go? So we first write interaction term in Schrödinger equation. What is this? We discussed it once. It's a sum of all particle pairs, and there is a contribution to energy coming from each pair of the particles. Pairwise interaction. Fine. And what I want to do with this, it's actually a sum over particle coordinates. Let me rewrite in terms of the density. It just gives delta functions at the coordinates of the particles. All right? Do you understand what I mean? It's a function which is delta function at all particle coordinates, density of the particles. Right, so instead of summation, I can replace it with integration. Good. So I have two particle densities here and here. That's logical. The only point I would like to exclude the cases when particle needs to interact with itself. All right. Look, just in this term, I eventually thrown away the terms with where I equal j. A particle doesn't interact with itself, so I have to do it here. Good. We have it now in terms of densities. Now let us replace the densities with what we know is field operators. All right. And that would be first density, and for the second density, as I said, I need to exchange, I need to add this delta function. That I can do with commutation rule. So I end up with this order of operators. Good. In this case, all annihilation operators are on the right from creation operators. So if it works on the vacuum, it doesn't give rise to an energy. Yeah, that's logical because there are no particles there. Fine. Now I want to make it in the level representation and in a particular system of levels, which are plane waves. In other words, I want to get it in wave vector representation. How one can do this? One can run Fourier transform of all these functions. So why we can say that rho equals rho hood. Okay, hat even. Good. Why we replace density by an operator? It is, if you wish, the procedure of a second quantization. So it's not a formal derivation. There is some postulating in it that we replace classical value by operator and kind of don't care about this. But one can check that it is consistent definition after all. Okay. The same we do with the Hamiltonian. We start with energy, which is a number, and we promoted it into an operator. Fine, good. So I want to get this coordinate operating coordinate representation from coordinate representation to wave vector representation. In this case, I kind of need to substitute for each field operator its expression in terms of, let me take this one, in terms of operator AK, right? In this case, into summation over K. Okay, this is replacement for this particular operator. I have to do it with all. I have to take care of this, all these exponents which arise in this expression, and integrate these exponents over coordinates. So what I got is eventually a logical thing. I got conservation of momentum. All right. So let's see what I have here. I have annihilated particles with K and K prime, and creation of particles with the same sum of two vectors. The total wave vector of two particles is the same. Some momentum is transferred from one particle to another particle, momentum Q, and that is expressed with a Fourier component of this potential. Okay, just wave vector representation. To do this, one needs to substitute wave functions in this form and perform the integration. But, well, it's also logical, and I will show you a picture about this. Come kind of diagram I do. So how to kind of understood this term, memorize it, how to draw it. These two, this can be regarded as a term which scatters particles with certain k vector, right? Suppose initially we have a state with two such particles, k and k prime. What does this term do? It kills these particles. And instead of that, it creates two new particles, which have, again, the same total momentum. Momentum is conserved. But there is a transfer of momentum from one particle to another particle. There's an amplitude which is given by Fourier component of the potential. So it can be regarded as a scattering of two particles with momentum exchange Q. All right, that's what I said about interaction. Let us see. Let me talk about field operators in Heisenberg picture. Right? We have recently recalled or whatever learned Heisenberg picture. And as we know that in this picture, in contrast to Schrödinger picture, wave functions do not change at all. They kind of fixed in the time of creation of the universe. Right? Instead, the operators do change. For any operator, the equation of motion is this, it's just commutation of this operator with a Hamiltonian. This is very contrast picture with respect to Schrödinger one. Good, recall this. Let us just see how does it go in for our particular operators, for field operators. Let us see. Let us just talk about the creation operators and annihilation operators in level representation. We would also assume that there's no interaction, otherwise it gets too complex. So we need to commute operator A with operator of one here stays for single particle. Good. If you perform all these commutations, it used to be an exercise for you to derive it by yourself. I believe it's still in the book. Right. Then we end up with this expression. So time derivative of annihilation operator, just the operator itself times energy. Simple equation. If you think it's too simple, you can make it a little bit more complicated. Recognize that it's eventually Hamiltonian equation. It's a Hamiltonian, single particle Hamiltonian, which comes here. So we can rewrite it for field operators in coordinate representation. And we see what we see is a time derivative of the operator, that's fine. And the Hamiltonian, which works in this way at this operator. Multiplication is VR, second derivative, but it doesn't work on the wave function. It does this with operator. Confusingly enough, if you just remove the head, you recognize this equation. If you remove the head, It's just the same Schrödinger equation, non-stationary Schrödinger equation. That is the origin of the term of the second quantization. Right? Let us write these two equations again next to each other. This is a Schrödinger equation for for a wave function. If we consider the same Hamiltonian but just put some particles in it, we can describe the situation with field operators. And Heisenberg equation for the field operator would be equivalent to the Schrödinger equation. And it looks like we have quantized the wave function. It looks like we have replaced wave function by an operator. Nothing of the kind. It's better to do the following. We don't have already derivation of particles because we don't have single particles. Rather, we have a field. Remember, field, which describes these particles. A field which persists everywhere in the whole galaxy. And this is the dynamical equation for the field. Field is an operator, quantum object. One could think of classical approximation to this field equation. We can kind of average this operator over the wave function. As you remember, wave function stays the same. One can think of expectation value of this operator. Well, if we do so, well, obviously we got the equation for a function. So it is better to regard this equation as a classical field equation. Equation for classical field, quantum field as an operator, classical field is just function, which depends on coordinate and time. And okay, that's an equation this field obeys. Good. This is more or less about the origin of this term of second quantization. But don't be confused. It's not wave function which is quantized. Rather, the equation which describes the field theory, one can say, appears to be formally similar to Schrödinger equation for a single particle. But single particles are gone. We have a single field. Good. Oh, there are no questions about this. I thought it was a complex material, but oh, I guess it went good. Let's just see. I have to speed up a bit because I still have to talk about fermions. Or I shouldn't say have to. I really enjoy talking about fermions. I like fermions even more than bosons. Right. It's yeah. I don't think it's important. Just yet another explanation of second quantization. Let me talk about fermions, and you see the outline of this fermion part is almost exactly the same as for bosons. Anyway, we will introduce creation and annihilation operators. We derive occupation numbers. We will look at the structure of the Fock space, field operators, Hamiltonian, field operators, Heisenberg computation, almost the same set of topics with only a few differences, some of them important. So I hope I can finish all this in time. Right. What are the differences? First, it's a difference which is not really very important. We start with the basis of a single particle states, V number with index k. Examples a bit different. If one wave vector is not enough, because there's also spin for fermions, plus minus, two directions of spins. In any case, the basis states in the Fock space are labeled by a long row of occupation numbers. Each level gives rise to a number. The only point we are working with fermions, so these numbers are either 0 or 1. To understand what is to talk about anti-commutation, it's a bit counterintuitive subject. Let me use another representation of the same row. So instead of writing 0, 1, 1, 0, whatever, I will just concentrate on the sequence of occupied states. So here level 2, level 3, level 5, they are occupied. Fine. And now I can imagine that I have another sequence of states. Instead of 3, 5, I will put 5 and 3. And I also need to recall that wave function is anti-symmetric. So if I change the sequences, I would have to change the sign because it corresponds to, remember what, permutation of particles. And that is causes a requirement. Let's see that for requirement. So we are its goal is to make a creation operator. Here it is. I'd like to create a fermion at the level k and at the level k prime. But in order to make sure that the function is anti-symmetric, I need to say that if I put these operators in an opposite order, I will have different sign. So anti-symmetry of Fermion equation imposes this strange condition on the form of creation operators. As you see, they are not commuting, rather they entire commute. Let's see. Now I'm ready to give the definition of annihilation operator for Fermions. It's a bit tricky. As annihilation operator for bosons, it does the same. It removes one particle from the state K if K is occupied. Right? K can have two particles, right? On the one So it works on this particular state. And it returns the state without the particle with a funny factor. This factor can be only plus or minus 1 because it kind of solves this problem with sign dimension, right? But it depends on all occupation numbers for the levels which are before level K. That makes this operator unphysical. And I wonder if somebody can tell me why.
It depends on the state.
That is common. Any operator, since we describe the action of operator on a state. Of course, the result depends on the state. No.
No, but the operator itself depends on the state, or not.
But we are talking about action of this operator on a particular state. It depends on the state. That's fine. That can be with any physical operator.
I think if you would write the state in the other way, you could not really defend writing it one way or the other.
Yeah, that's close to right answer. Look, in order to write this row, we have chosen the certain order of levels. But this order is only for us. It's this order is in our head. It's not physical. One can, for instance, order levels in order of energy. One can choose any different order. It's arbitrary. It's up to us. And it appears that the definition of the separator does depend on our completely subjective choice. So in this sense, it is unphysical. From the other hand, there are many examples of unphysical values like voltage. Yeah? You can say what is a voltage in a given point of space. You can talk only about voltage differences. And to define voltage in a point of a space, it's up to us. We can add any constant. So there's nothing wrong with some values being unphysical. All right? As far as we can make with them physical values, things which can be observed. But we cannot observe really matrix elements of creation operator because it depends on our subjective choice. Fine. So let us try to get something physical to that. First of all, I would, let's see, I guess it's repetition of slides. What does the conjugated operator do? Well, it is the same as with operators of the bosons. It creates a particle. It creates a particle from 0, you get 1. Same factor appears. All sum of all occupation numbers, either even number of or odd number of particles before the given level. let us now get the physical values. Let us compute occupation numbers. So we, as for bosons, we look at the products of these operators. Good, sir. It's a little bit tedious calculation. Right, so in this case, one has to, yeah, basically apply this factor. So this state is obviation. We add the particles. This factor requires some evaporation. But all this evaporation disappears if we let's see, if we change the order, right? We can compare this to orders, and we got the same factor apart from factor of -1. So we conclude we have compared this real calculation that initial idea works. We have managed to make these operators to anti-commute like this. Same one can get for conjugation operators. Now we want to look at product C, dagger C. Again, all these factors. Oh, something that is my window. Sometimes Zoom, I guess I need to stop share for a second. Sometimes Zoom makes very crazy things with Windows. Here we are. So for the same K and K prime, we got occupation numbers. It depends on the order of operator, whether we have n or 1 minus n. It means that these operators anti-commute except the same state, except k equals k prime. Good. With this, we can we have occupation number. We have total number of particles. That's precisely as for bosons. And as for bosons, we could use these commutation rules, postulate them, and then figure out that with these operators we can make the whole Fock space. All right. So let's just to show anti-commutation for let's see, I guess I go wrong direction. Okay, now let us make all states with Fock space with these operators that we have already done with bosons. Right, and that is pretty simple at first sight, at least. So we just figure out what particles we have to create in which levels, and we apply the separators. No operator comes twice. eventually to guarantee that we cannot create this particle, C dagger squared equals, you can help me.
Should it just be C dagger or identity? Then you can't create more because you can only have one in every level. So shouldn't.
If it were identity, look what would happen. You create fermion twice, you get the same wave function. Nothing would change. No.
In that case,
something
that
different.
equals the C dagger.
What did you say?
Just C dagger, so it just adds one particle as many times.
No, in this case, yeah.
0.
Actually, this is very specific for this particular course of advanced quantum mechanics. If I ask you something, most probably the answer is 0. There are lots of zeros in quantum mechanics, and in near future we'll make a very good use of this. It is 0. Again, it's the same as vacuum. If you cannot do something with a wave function, it gives you 0. Application of the separator gives you no wave function, unnormalized vector in Hilbert space. Right, in vacuum we could not annihilate, right? So if you apply the separator to 0, it is 0. Creation of two fermions at the same time gives you 0 for all possible states. Good. Otherwise, it's nice formula. We can create all number states by application of certain number of creation operators. Right, so let's get to the same example as for bosons. Two levels, two-dimensional space. Now we see there's some difference. We can go from state 0, 0 to state 1, 1 in two different ways. First creating in the second level, and then creating in the first creating in the first level, and then creating in the second level. Or otherwise, first creating in the second level, and then in the first level. And this, as we discussed, they actually give rise to different wave functions. Difference is in the sign. Well, otherwise you could navigate with these operators as freely as with bosons, and one could also set up web pages for this. Perhaps I should create such a site. It might be my contribution to pedagogical science about Fock space. Right, so that's how it works. Let us see. Field operators. Field operators, here the issue of spin comes about. One could think of spinless fermions in coordinate space, but it's rather practical. Usually fermions do have spin. So we not only create annihilate, okay, it's annihilation operator. We not only annihilate a particle at the point R, we annihilate it with a certain spin. Fine. Right, all kind of simple machinery around is precisely the same as for bosonic operators. So instead of repeating this, I just write similar formulas. As you see, the difference only in summation over spin. Right. Particle scattering can be interesting. Do I have a picture like this? No. Now, particle scattering is very interesting. It conserves spin, right? So you see same spin indices here, here, and here. So spin of the particle does not change in course of this scattering. Good. What else? equation for field operators is the same as Schrödinger equation, apart from the fact that it contains spin. So it looks like Schrödinger equation for two-component wave function that, as we discussed, it is not. Rather, this is a dynamical equation for a field, dynamical equation for a linear field, and not for wave function of anything. Good. So I am done with Fermions. I did that rather quickly, but this is because I basically have repeated most steps I have already done for bosons. And you see that answers are very similar. To put all differences and similarities together, I have made a table which I want to talk about now. So it's a summary of last two lectures. Let's go for that. So have rows and two columns for bosons and fermions. First of all, wave function of basis states. They must be symmetric for bosonic particles. They must be antisymmetric for fermion particles. Right. In any case, we can make a Fock space, either for bosons or fermions, so we can combine Fock spaces for bosons and for fermions in a single Fock space. Basis states are labeled by sets of occupation numbers. So a set of occupation numbers uniquely defines the basis state in Fock space. Fine occupation numbers are integer. It has to be integer. It's number of particles, non-negative. For fermions, owing to anti-symmetry of wave functions, they are restricted to 0 and 1. Fine. That was more or less the lecture a week ago. Let's come to today's lecture. Annihilation creation operators. We have a system of levels labeled by K. It could be a wave vector. It doesn't have to be. Any basis in a single particle space would suffice. For bosons, we have commutation relations. They do commute at different levels, and A and A dagger creation relation does not commute at the same level. For fermions, it's somewhat the same, but there is a very important replacement. Instead of commutator, we talk about anti-commutator. Then they anti-commute for all, in any case, for different levels, right? But this anti-commutation rule is broken at the same level for operator A dagger A. This we need in order to represent, how they call it, occupation number. Fine. Field operator. From the operators in level representation, we can go to any other representation. Convenient representation is coordinate representation. Here's the field operator. Formally, I would put also sigma here for fermions, but yeah, I just for simplicity, I didn't do this. Field operators. What else? Yeah. Example, Hamiltonian for a uniform system. Uniform system in this case means that momentum is conserved and particles in empty space. Look, it consists of single particle energy, and we also have interaction. And apart from indices, it is the same for bosons and fermions. Let's pay attention to the fact that without interaction, we always have pairs of creation-annihilation operators. Interaction gives rise to more complex products starting from 4. Heisenberg equation. For both cases, it is the same as Schrödinger equation for the wave function. Sure, I'm done with the second quantization, and that gives us all tools we need for this course, Advanced Quantum Mechanics. Of course, if you just get a tool, you need to practice with this tool in order to make your work efficient. Remember first time you took a hammer, right? So please be careful with your fingers. It's a very powerful technique. To start this work, to start familiarizing yourself with the technique, I will release homework. Many people who were eager to do homework for this course, today you finally get the chance. Right, so I will release homework problems. There is, let me say a couple of words about homework. There are each homework problem, if I remember correctly, consists of 5 points. It is structured as a usual example problem. The last exam problem, the last point is bonus point. And it is written how many score points this bonus point would give to you. If you take the first problem, you would read that the full solution of the bonus point brings you 75 score points, which is about a half of the total homework score. This is to indicate how much time would it require for you to make this. So be careful with this. Plan your time. Right. Otherwise, I think the homework is a kind of self-explanatory. We did our best to make it comprehensive in such a way that you can solve a particular problem, a particular task, point by point. Let's see. There's a question. Oh Jesus! I guess I've lost the chart. Let us see. It's due in a month, correct? I don't remember exact date. It must be about this, right? It's closer to the end of semester. So you have ample time to work on this. There will be also a session with supervised homework. Good. Oh, I'm still recording. I should have stopped this.